Hello, everyone. Today I would like to go over a few concepts related to matter and mixtures and a variety of changes with energy. So, first of all, let's talk a little bit about the concept of matter and the differences between physical and chemical properties. So, we know, of course, that matter is easily and for our purposes described as anything that has mass, right, and takes up space. In this case, we also have some other qualities. Matter can be observed as being an element, pure, if you will. Pure. And this matter that consists of just one item. So this would be single material. And this kind of single material can be composed of items such as a single element, or it can be a single compound. And in all those cases, we also have the possibilities that we have a variety of mixing these. So we also have mixtures. And mixtures, of course, are two or more substances. Not chemically combined, two or more substances that are not chemically combined. And we can have a couple of different kinds of mixtures. We can have homogeneous, which means everything is evenly distributed. Or we can have heterogeneous, which means things exist in a mixture that is not evenly distributed. So a homogeneous mixture, an example might be salt in water. Does make any difference whether you taste the top of a glass of salty water or the bottom. It's the same mixture. Another example of a heterogeneous would be, as an example here, might be something like sand and water. Oops. And sand and water, of course, has a variety of sizes. Some of them that are very large will be, of course, at the bottom of the glass. Some that are the same, that are relatively small and almost the same density as water, will be somewhere in the middle. And those that are less dense than water particles will be floating on top. Okay. So we have single element or single compound. We have mixtures. Let's make sure that we understand the other concept here. Of course, we have compounds. Let me put element first. Element is substance, right? Consists of only one type of atom. And a compound is a substance that consists of two or more different atoms, atom types. combined, chemically combined. In other words, they share electrons. So in this case, we are examining two different types of materials that are both pure. Elements are pure and compounds are pure. Certainly an example of an element example, you might look at something like aluminum. Spell right. A compound example would be something like water. Because you can have pure aluminum, you can have pure water. Okay, so the composition of these materials can change if we mix them or we cause a reaction to happen. And so in doing so, what we would apply here are the issues related to energy. And what I want to do is just highlight a couple of things related to energy. Energy is oftentimes expressed as the ability to work, but we can look at energy that is supplied as heat, for example, and in doing so, we can look at the absorption of energy and the conditions under which we are applying this and what the results are. For example, if we look at one type of energy, let's take heat energy for a moment. If we take some water, of course, you know water is H2O, and it exists as a liquid typically, right? That's L stands for liquid. If we apply some heat energy to it, this delta is telling us that we're heating it. We can take the water and start with its form as a liquid and end up with water as a gas. Now what we've done here is had a phase change. So we had water as a liquid, and of course we heat it, and we get water as a gas. This is a phase change. It takes a certain amount of energy to do this, and for each gram of water, it's unique in the amount of energy water takes as opposed to something to raise water 1 degree Celsius or to even induce it to change into a gas from a certain temperature to another temperature. If we had something else other than water, if we had, for example, alcohol and we heated it, it would take a different amount of energy. So all of these require various amounts of energy, and this phase change is also maintaining the chemical structure of the water, so the chemical structure did not change, and this is known as a physical change. Now, other types of physical changes are, for example, if we take a piece of carbon and grind it down to tiny fine particles, that's also physical change because it's still carbon. If we take a material and freeze it, such as making it into liquid into ice in terms of water, it's still a physical change because it's still H2O. Now, we can also put in more heat energy, or we can use electrical energy. For example, again, let's go back to water. If we take water and we apply electrical energy to it, like an electrolysis, that's the symbol for electrolysis, we can get hydrogen gas plus oxygen gas. And if we put 2 of these here, then we'll put 2 of these here. And I notice what's happened here is we now have a chemical change. We start off with pure water, and we end up with two elements that compose the water. We end up with hydrogen, and we end up with oxygen. And by the way, you notice that the hydrogen and the oxygen occur as what's known as diatomic molecules. We have H2 for hydrogen and O2 for oxygen, indicating that the compound is known to exist as hydrogen containing 2 atoms of hydrogen to make hydrogen gas and 2 atoms of oxygen to make stable oxygen gas. And each of these was made from the molecules of water, which contain hydrogen and oxygen. Okay, so that's a chemical change. It's not the same thing anymore in terms of the products, which are on this side. And here's the reactants. We'll call these reactants. And these are known as products. So what we have here is a change in structure that is not reversible, in the sense that if we just simply drop the temperature or do something in that sense, we can put this together very easily. We actually have to have a chemical reaction occur. By the way, you can do this with heat. It just turns out that the heat that you would need, if we did it with heat, it would be something in the vicinity of 2,000 degrees Celsius before we could actually get it done. That's why the electrical current is so much more efficient. Okay. So here we have a process in which we have physical change and another process with more energy undergoing chemical change. Now, what I want to talk a little bit more about is concepts here related to the structures of these materials as atoms, and a little bit more about how to make sure that you understand calculations that are involved in heating and cooling and in reactions. So let's take a moment and examine the concepts behind the process of energy and absorption of heat and temperature changes. So in your text, you have a discussion related to an item known as heat capacity and specific heat. So I want to focus on specific heat for a moment. So specific heat is really a measurement and a description of energy. This is the amount of heat energy, and this is typically expressed in either calories or joules, and it is related to the amount of energy it takes to raise the temperature of an item 1 degree Celsius for each gram. So, for example, the specific heat of energy calories required to raise the temperature of 1 gram of a material 1 degree Celsius. So for water, for example, if we find specific heat in the context of heating water, we'll find that this process is pretty straightforward in terms of expressing the energy required. So we could say for water, if we took the measurement, we find that the specific heat, the heat energy, specific heat for H2O equals the energy required to raise 1 calorie of water 1 degree Celsius. So we have specific heat of water is 1 calorie to raise 1 gram of water 1 degree Celsius. So what this says in effect, it defines a calorie for us. Well, what this says is if we have this 1 gram of water, let's say it's right here, and we are raising this from 35 degrees Celsius, let's say this is H2O liquid, right? And we're going to add some energy to it, and we're still going to have H2O liquid here, and we've got it in this box. It's going to 36 degrees Celsius. If we had 1 gram of this material here and 1 gram of this material here, it would require 1 calorie of energy, heat energy, to take it up 1 degree. Turns out that that is a convenient definition of a calorie. Specific heat also for water can be defined as joules. It's just another form of measurement for heat. For H2O here is equal to 4.184 joules for every 1 gram to be raised 1 degree Celsius, and that's just for water. And obviously, if we had something like a piece of copper, it would be different. If we had a piece of gold, it would be different. And if we had ice, it's different than it is with liquid water as opposed to the other types of steps. For example, if you had steam, it would be different. It is dependent upon what the phase is, solid, liquid, or gas. It also depends upon very much what the material is. So how do we use this information? Well, for example, if we had 100 grams of water and we wanted to raise it from 43 degrees Celsius, so 100 grams of water at 43 degrees Celsius, and we want to take it to, let's say, 50 degrees Celsius. How much energy does it take? So how many calories of heat energy will this require? So you could set it up by saying, well, let's define a few things. So we'll call Q equal to calories. So this could be, of course, heat energy. And, of course, we need another item called delta T. It's the change in temperature. Delta means change. Change in temperature. And of course, we have the degrees Celsius, which typically what we're working with, although we could work with other situations also. But the process is fairly straightforward. What you know is that the specific heat of water, so let's call specific heat of water is equal to 1 calorie required to change the temperature of 1 gram of water 1 degree Celsius. Now the general form here is to tell you that the heat energy, so this would be calories. This is, of course, calories, Q. So calories required to change 1 gram of water, right, or 1 gram of anything. We'll call it mass over here. and this is in grams, multiplied by this, which is, we'll call it delta T. Now, this really means temperature final minus temperature initial. So we're going from one temperature to another temperature. So in this case, if we change and take a look at all the pieces, it turns out that this, for water, always must be held true as long as the water is in a liquid phase. So if we now know that we have 1 calorie, right, per 1 gram, and we're changing the temperature 1 degree Celsius, that has to equal some unknown number of calories. It's called Q. And how many grams do we have? Well, over here, I think we said we had 100 grams. And the change in temperature, the initial temperature was 43 and the final temperature is 50. So we'd say 50 degrees Celsius minus 43 degrees Celsius, because we're raising the temperature here. So now, of course, this is going to equal some number of calories divided by 100 grams, and this, of course, now comes up to 7 degrees Celsius. And this has to equal 1 calorie for every 1 gram per 1 degree Celsius. So how do we find the total number of calories? Well, that's right here. So if we multiply both sides by 100 grams and 7 degrees, so we get 1 calorie per 1 gram per 1 degree Celsius times 100 grams times 7 degrees Celsius over 1 in this case has to equal, of course, Q over 100 grams times 7 degrees Celsius. And this again is also multiplied by 100 grams times 7 degrees Celsius. And of course, these are going to cancel out completely. So we have Q here. And what we're looking at is grams canceling with grams, degrees Celsius canceling with degrees Celsius. So what we have in the end is 7, we have here 7 times 100 times 1, so we have 700 calories. It's going to be required to heat that 100 grams of water 7 degrees Celsius. And that would hold the same if we were to use joules instead of calories and work with 4.184 instead of 1 calorie per 1 gram. One other point, the calorie that you see in dieting and nutritional values is equal to 1,000 calories of the type that we're defining, which is also known as 1 kilocalorie, which is also written as 1 kcal. So just so you know how these process steps fit in terms of nomenclature. So just to emphasize something, if we had a piece of metal, let's say we had 25 grams of some metal, doesn't make any difference which one, and let's say that its specific heat was equal to 0.105, and we'll put this time as joules per 1 gram per 1 degree Celsius. So this simply means that it takes 0.105 joules of energy to raise this 1 gram of this metal 1 degree Celsius. So if we had 200 grams of this metal, right? And we're going to heat it from, let's say, 50 degrees Celsius all the way to 100 degrees Celsius. And what we want to know is how many joules of energy is this going to require. We simply use the same process we did earlier, and the setup would be the same. So we would say 0.105 joules are required for every 1 gram to be raised 1 degree Celsius. That has to equal the number of joules that we're looking for, which we don't know. And we have 200 grams of this material metal. And we're going to raise it from 50 to 100. So obviously it's 50 degrees difference. So it's going to require the absorption of 50 degrees of change in temperature. It's going to require 50 degree change in temperature. So again, we do the same thing, repeat the process, and we're going to be looking for joules. So if we just shorten some of the arithmetic here, so we say 0.105 joules per 1 gram per 1 degree Celsius times 200 grams, so 1 times 50.0 degrees Celsius. So 1 has to equal the number of joules. So if we go through this process and simply do straightforward multiplication, we would have 0.105 times 200 times 50, and that gives us 1,050 joules. We have 3 sig figs here, so we'll have to adjust this in a minute. But we can do this. We can also say that this is 1.050 kilojoules, same idea as we had joules. And of course, since we have only 3 sig figs, it would be 1.05 kilojoules is the amount of energy it would take. Now, you should notice something, that the smaller the number is for the specific heat, the easier it is to raise the temperature. So if we have a 1 gram of this metal at which has a specific heat of 0.105 joules per gram degree Celsius versus 1 gram of H2O, which takes 4.184 joules per 1 gram per 1 degree Celsius. You should recognize, of course, that it's easier to heat up a piece of metal the same size than it would be to heat up the same mass of water and move it to the same temperature. So what it's saying is, in effect, that metals and certain other items absorb heat faster and transmit heat faster than water does. Water retains temperature once you heat it up longer, but it takes more energy to change the temperature. So that's something to keep in mind with respect to how the physical changes in raising the temperature of water versus raising the temperature of something like metal. Okay.